In this video, we'll cover stoichiometric calculation. Whenever we hear the word stoichiometry, we're talking about the studies of material consumed and produced in a chemical reaction. For example, say you have 1 gram of hydrogen and another gram of oxygen. Then in the end, how much water will be produced in the end? Or say you want to produce 4 moles of water, how many molecules of oxygens and hydrogens do we need? These amount, the quantities, amount of how many, how much, and the calculation that involves between a product and a reactant. This whole entire section is based on what is called the stoichiometry. So now we're going to go into a little more details by solving the problem in itself. Let's go into this equation here, this chemical equation. It shows that there's H2 and O2 that forms water. So very first thing you want to do is you're going to balance the equation. So try balancing this equation so that the left side of the reactant and the product is equal in same amount of elements. So try that and then come back and we'll dive into calculation. So here is the balance equation. So you needed to put the 2 coefficient in front of the H2 and 2 in front of the H2O. Here you can generate various different types of unit conversion based on the balance equation alone. And there are as follows. If I just look at the reactant, I can write 2 moles of H2 over 1 mole of O2. So I'm only looking at the reactant, or I could flip it and write it the other way around, where I have 1 mole of O2 all over 2 moles of H2. Okay. We can also compare between the reactant and the product as well. So let's see, 1 mole of O2 all over 2 moles of H2O, or you can write this as 2 moles of H2O all over 1 mole of O2. What about in comparison to hydrogen? Yes, we can do that. So 2 moles of hydrogen for every 2 moles of H2O, or 2 moles of H2O on top and the other one goes on the bottom. So you have generated 6 different unit conversion based on this balance equation alone. And I consider this as mole to mole, okay? Mole to mole ratio. Now, why is this significant of mole to mole ratio? And that's because of the following example question. It says, how many moles of O2 are required to react with 0.429 moles of hydrogen according to the following equation? So you already balanced the equation and you have all these setups over here on the side. And so what you're going to do is go ahead and start off with the problem, which the given problem, which is 0.429 moles of H2, and leave a big space, and then you want to make it equal to, what are we looking for? We're looking for moles of O2, so I want my unit to be moles of O2 in the end. Now, let's look at all of the possibility choices on this side over here. Which one of these has to be used in order to cross cancel out the moles of hydrogen, and so that you're left with also moles of oxygen? Here, I'm going to use this one right here. The one that says moles of oxygen on top and 2 moles of hydrogen on the bottom. I will utilize this mole to mole ratio and place it in here. Why did I do that? That's because so I could cancel out the moles of hydrogen, and here's moles of hydrogen. And then you're left with 1 mole of oxygen, and that's the unit we want. We want moles of oxygen to be left over. So let's go ahead and do the calculation in your calculator. So take out your calculator, and probably a good time to take out your reference sheet as well. So the calculator says 0.429, multiply that by 1, and then you're going to hit enter. Then you will divide by 2, because it says 2 moles on the bottom, and then hit enter. The calculator spits out 0.2145. Notice that this problem is 3 significant figures. It starts with 3 significant figures, so we want to end with 3 sig figs. So here it's 0.215 moles of oxygen. It should be the final answer. Okay. So notice what we did so far. We balanced the equation, then we looked for some conversion factors, then we set up the equation to find out the calculation in the end. So let's do another problem here. I'll come back to those steps in a moment. Here it says, how many moles of I2 are required to react with 0.429 moles of aluminum according to the equation? To prevent you from being confused, this right here is I2. So that's I2. Sometimes it looks a little different. And this is AL I3. So balance this equation and then come back. So here is the balanced equation, 2 to 3 to 2. Now let's dive into the some of the potential mole-to-mole ratio that could come from here. If you can try and see if you can come up with all of the 6 possible mole-to-mole ratio, try that and come back. I'm going to pause this video and then I will show it all up at once. So here are all the possible mole-to-mole ratio that is generated from this balanced equation. So the question asks 0.429 moles of aluminum are given, and from that, with this reaction, how many moles of I2 is required to produce a product? So in the end, I want moles of I2. So based on this, the relationship that's showing in the equation is between I2 and aluminum. So where in this conversion mole-to-mole ratio shows the relationship between I2 and Al2? Well, it looks like this row right here, I2 and Al2, I2 and Al2. Now, Al. Now, which one am I going to use in order to cancel out the aluminum? And then, so you have iodine left over. Hopefully, you were able to select the second one, this one right here. And that's because the aluminum goes on the bottom and iodine goes on top. So moles of aluminum cancels out, and then we can calculate this out. So go ahead and calculate this out and then try and come back and see if you got the right answer. It is recorded in 3 sig figs. So the problem starts with 3 sig figs. This is a multiplication division type of problem. You leave it with 3 sig figs in the end. So that's your answer. It means that it requires 0.644 moles of iodine to react with the aluminum. Let's do another one. Here, I'm going to take it up a notch. The question asks how many NH3 molecules, not moles, molecules are produced by the reaction of 4.0 moles of calcium hydroxide according to the following balanced equation. So this equation is already balanced. This chemical equation, you don't need to put any more coefficient. The only coefficient that's shown here is 2. The rest are 1. So let's start with thinking about it for a moment. You start off with 4.0 moles of calcium hydroxide. And then you want to do a lot of calculation, or maybe some calculation, so that you end up with NH molecules of NH3. Okay. Now, in order to get to there, let's think about the mole-to-mole ratio. To find all the possible mole-to-mole ratio for this chemical equation, you can actually write them out, but they're quite long, and it's useless to write everything. As in previous problems, we only used one of the mole-to-mole ratio. We didn't use all of the possibilities. So here, look at the relationship between NH3 and calcium hydroxide, since that's the relationship that we're looking for right now. We're looking for a conversion from calcium hydroxide to NH3. So in the balanced equation, you're going to look at the relationship between calcium hydroxide and NH3. So if I do the unit conversion factor from those generated from those two compounds, it's every 1 mole of calcium hydroxide is 2 moles of NH3, or 2 moles of NH3 all over 1 mole of calcium hydroxide. Okay, now that we have mole-to-mole ratio, let's kind of dive in a little bit. Notice that it starts with the moles of calcium hydroxide. In order for me to cancel out the calcium hydroxide, I am going to take which one? The second one. 1 mole of calcium hydroxide, and then 2 moles of NH3. Great. The calcium hydroxide mole-to-mole ratio has been canceled, and now I'm left with moles of NH3. That still doesn't lead me to the molecules of NH3. If we recall in a different video, you should have thought there was a video regarding Avogadro's number. And in that Avogadro's number, we said anything 1 mole of any element or compound or anything is equal to 6.022 times 10 to the 23 molecules or atoms or formula units. Here, I'll go ahead and utilize molecules of NH3. From here, two potential unit conversion factor has been generated. 1 mole over whatever it is times 10 to the 23rd molecules, or the molecules went top. Or 1 mole. And here, you notice that we need to cancel out the moles. Because we need to cancel out the moles, we're going to go ahead and put the one that says moles on the bottom. 1 mole of what? 1 mole of NH3. And we're looking at 6.022 times 10 to the 23rd molecules of NH3. The mole to mole cancels out. So let's recap. We know that there is mole to mole ratio, okay, that's represented as shown on the screen as brown. And then we have this Avogadro's number, right? Potentially whether the molecule goes on top or the mole goes on the bottom or the other way around, that's in green. And those are the two possible conversion factors that can be utilized in order to do the calculation here. So let's go ahead. We utilize mole to mole and then molecules to mole. Let's do this in the calculator. So here's my calculator. 4.0, let's take care of everything on the top, times 2, okay, times, and then anytime you see this big Avogadro's number, you're going to multiply that by, with the open parentheses, 6.022 times 10 to the 23rd, close the parentheses, then hit enter. After you hit enter, you're going to take care of everything that's on the bottom. So divide it by, open up a parentheses, 1 times the 1, which should get you to the same thing. So the correct answer is, well, the calculator says 4.8 times 10 to the 24. I only put 4.8 because this starts with 2 sig figs. So I should end up with 2 sig figs. And the unit is molecules of NH3. Let me rewrite this so that it's not so confusing. I'm going to rewrite the answer. The answer is 4.8 times 10 to the 24th molecules. NH3.